All right, let's talk about something every data scientist runs into. You've just run your clustering algorithm, and now you're staring at the results. So what's next? How do you actually know if the groups it found are any good?
So you've done the hard part, right? You've fed your data into an algorithm, maybe it was k-means or dbScan, and boom, it spits out these neat-looking clusters. And it feels like a victory, for sure, but this is where the real work actually begins.
The next, and honestly most critical step, is to ask a simple question. Are these clusters meaningful? Do they tell a real story about the data, or are they just random groupings? In other words, are they any good at all? Well, evaluation is how we find out.
To make this super clear, let's use an analogy. Imagine you're handed a toolbox that's an absolute disaster. Your job is to sort everything inside. But here's the catch. You have 0 instructions. This, right here, is the clustering conundrum.
And that's really what clustering is. It's an unsupervised task, which is just a fancy way of saying there's no answer key. You're just taking a jumble of data points, all your nuts, bolts, screws, and wrenches, and trying to create sensible piles based on what's similar.
So you've made your piles. You've got screwdrivers over here, hammers over there. It definitely looks organized. But how can you be sure? How do you know you've made the best, most logical groups you possibly could? How do you actually measure the quality of your sort?
Okay, so the first way to tackle this is to judge your work from the inside. We call this internal evaluation, and it's what we have to rely on when we don't have that answer key. We can only use the data itself to figure out how well we did.
Internally, we're really looking for 2 main things. First, cohesion. Are the items inside each pile really similar to each other? Are all the screwdrivers actually screwdrivers? And second, separation. Are the different piles clearly distinct? Is your screwdriver pile very, very different from your hammer pile? Good clusters have a ton of both. Now, one of the best tools for this job is something called the silhouette score. It's a really clever metric that basically asks a simple, intuitive question for every single data point. Is this point happier where it is, or would it be a better fit with its neighbors in another cluster? So if you get a high score, something close to +1, that's fantastic news. It means a data point is a great fit for its own group and a terrible fit for any other. It's right where it belongs. That's a good sort. But a negative score? That's a huge red flag. A negative score is basically telling you that a data point is actually closer, on average, to the points in a neighboring cluster. It's a clear signal that it might be in the completely wrong group.
Okay, but what if we get lucky? What if sometimes we do have an answer key, a blueprint we can check our work against? Well, this is where external evaluation comes in. In data science, we call this blueprint ground truth. These are correct pre-existing labels for our data. Think of it like getting the original manufacturer's diagram for that messy toolbox. It shows you exactly where every single tool is supposed to go. So to compare our sorted piles to that blueprint, we use metrics like the Adjusted Rand Index, or ARI. It measures the similarity between the clusters we made and the ground truth labels. It's even smart enough to correct for the fact that you might get some right just by random chance. A perfect score of 1 means your clusters match the blueprint perfectly.
So we have our metrics, both for when we're flying blind and for when we have a map. But just knowing the tools isn't enough, right? Using them effectively, well, that's a craft. And there are some really important rules of thumb.
A truly robust evaluation goes way beyond just a single score. You have to consider a whole bunch of factors. For instance, your choice of distance metric. Are you using Euclidean for straight lines or cosine for angles? That alone can completely change the outcome. Then you've got the number of clusters you're looking for, their shapes, and even how much computing power it's going to take. Relying on just one number is a classic rookie mistake. A good analyst always looks at multiple metrics to get the full story.
And this brings us to probably the most common question in all of clustering. How do you pick K? The number of clusters. Is it 3? 5? Is it 100? How do you know?
While there's no single magic answer, thankfully we have metrics that can guide us. The Calinski-Harabasz index is a great example.
You can think of it as a score that gets higher when your clusters are really tight and dense, but also far apart from each other. So we look for the number of clusters that gives us the highest score. That's our sweet spot.
We've spent a lot of time on metrics, scores, and sorting toolboxes. But let's bring this all back to the real world. Why does getting this right actually matter so much?
Because in the real world, good clustering drives incredibly important decisions. For a marketing team, it's the difference between finding your real customers and just wasting millions of dollars. In bioinformatics, it can help validate life-saving genetic research. It's how social networks spot communities, and how self-driving cars understand the world. The stakes can be incredibly high.
And this brings us to a final, absolutely crucial point. These quantitative metrics are essential, no doubt about it, but they are not a substitute for your domain knowledge and your human expertise. They are a guide, not a verdict.
Which leaves us with this final thought. A metric will give you a score. You'll get an ARI of 0.8 or a silhouette score of 0.6, but you're the one who has to decide if that score is good enough to act on. For finding some rough customer groups, maybe a 0.6 is a huge breakthrough, but for medical imaging, anything less than a 0.9 could be a disaster. So the question isn't just about the score itself, it's about the context. It's about where you draw the line.